let's look at this question. So in this question, we need to calculate the maximum deflection of a uniformly loaded, simply supported beam shown here. So there is some numbers for the loading and for the span, but before we plug in those numbers for the span length or the loading, we can just get the expression for the deflections. So here we can using double integration method to get the maximum deflections. First of all, we need to come out the expression for bending moment. As we know, the double integration method using the moment curvature equation. The differential form of the moment curvature equation is showing here. So it's dy square dx square equal to moment over ei. Okay, so first of all, we need to know the bending moment. So from this loading scenario, we can calculate the reaction force is easily is at support A is QL over 2, support B is QL over 2. So we don't need to go to the details on that. So once we know the reaction force, we can draw the bending moment diagram. So first of all, we draw the shear force diagram. The shear force diagram is showing here. So this shear force diagram, the bending moment diagram, because the shear force is a linear curve, so the bending moment is a quadratic curve. So the slope of the bending moment is the value of the shear force. The value of shear force is positive on this half and negative on the right half. So we can draw the quadratic curve like this. So this is the bending moment. We can calculate the maximum bending moment is at the shear force equal to 0. So this is maximum bending moment. We can calculate that is QL square over 8. So this is maximum bending moment. So from this bending moment, we know we can just using one quadratic curve to express the bending moment. So now let's find the expression for the bending moment. If we just make a cut, arbitrary cut on the beam, if we see the cut is A to A, we draw the free body diagram. The free body diagram is showing here. So this is support A. We have reaction force QL over 2. The distributing load Q and distance is X. Okay, so this is the coordination systems, and we have shear force V and bending moment M on the cutting section. The cutting section is A to A. Okay, so if we write down the moment equation of equilibrium at the cutting section A to A, we have 2A equal to 0. This is the moment equation of equilibrium. So the positive is go to clockwise. So we can write down first of all is Q over 2 times the length of the segment is X. So it's go to clockwise, so it's positive. So the second bending moment is due to the distributing load on this beam segment. For this distributing load, we can first of all we need to calculate the point load, the equivalent point load, that is Qx. So Qx, the distance from Q, this equivalent load is X over 2. So we got, so this node have bending moment in counterclockwise, so it's negative Qx times X over 2. So this is second moment on the section A to A. the third moment is the moment m, internal bending moment m. So that's what we want to know. So it's m equal to 0. So we can come out the expression for the bending moment, that is 1 over 2 q x squared plus 1 over 2 q l x. So this is expression for the bending moment. Once we know the expression for the bending moment, we can plug in to this moment curvature equation, and we conduct first derivative, first integration, second integration, then we'll come out with the expression for the deflection. Okay, so here we have, so if we just move EI to the left hand side of the equation, we have EI, the second derivative of y, equal to bending moment. This is 2qx squared plus 1 over 2qlx. Now, on the first integration, we have EI y prime, so this is the first derivative, equal to, so I just write down the integration plus the 1 over 4 ql x squared plus c1. This is first integration. The second integration, EIY, is 1 over 24 qx to the fourth power plus qlx cubed plus c1x plus c2. So here we have two unknown constants. We have to apply the boundary conditions. So the boundary conditions we have, so at support A, the deflection is 0, and support B, deflection is 0. So we write down the boundary conditions, two boundary conditions at support A, x equal to 0, y equal to 0. So that is, so we plug in x equal to 0 into the deflection function, then we have c2 equal to 0 from this equation. The second boundary condition is x equal to L, y equal to 0. So this is second equation, and we plug in to this equation. We have 1 over 24 q L to the fourth plus and plus c1 L equal to 0. Then we got the expression for c1 is equal to minus 1 over 24 ql cubed. So we got c2, got c1, so we have the expression for the deflection, that is y equal to 1 over EI qx force plus 1 to have ql x cubed plus c. So here we have c1 is shown here, so it's 1 over 24 ql cubed x, and c2 equal to 0. So this is the expression for the deflection. For the slope, we got 1 over EI ql plus c1. So we got c1, the value is, just write down c1 over here, negative 1 over 24 ql cubed. So this is the slope. We got the deflection function, we got the slope function shown here. So now we need to find the maximum deflection. So we can easily find out the maximum deflection on this beam. On this case is just so we can easily know that it's just at the mid span. So at the mid span L/2. So we can find out that, but mathematically, if we want to find the maximum deflection, we have to find the slope equal to 0. Then we can find the maximum deflection. So if we want to know the slope equal to 0, so slope equation is here. So now slope equal to 0, then we got 1 over q x cubed plus 1 over 4 q l equal to 0. So if we say x equal to alpha l, okay, so then we got 1 over 2 q alpha cubed l cubed plus 1 over 4 q l alpha square l square 1 over 2 q l cubed equal to 0. So we can remove q because the q is a constant. Then we can also remove l cubed equal to 0. Then the equation will be the final equation with this. So we can find one of the solution is r equal to 1 over 2. So let us see at the mid span x equal to l over 2, we have the maximum deflection. The maximum deflection plugging l equal to x equal to l over 2, plugging this equation, we got the maximum deflection is 5q 384 EI. Okay, so then we can plug in the value of q of the span L of E and the moment of inertia into this expression. Then we got the maximum deflection. So I will introduce the procedure in next video. See you later.